Bueno, pues muy buenos días a todos. Sean todos bienvenidos. A nombre del Comité de Modelado Numérico, les agradezco mucho su interés y su presencia en este seminario. Eh, Les comento que la plática, bueno, el seminario de hoy va a ser dictado en inglés, pero pueden ustedes habilitar la opción de subtítulos por si les es necesario. Um, Thank you so much, Dr. Patrick, for making you some time for being here with us to share all your experience and research. Please feel very welcome.
Thank you very much.
Hola, soy Rafael Ortiz, también parte del Comité Numérico, y en este momento daré una pequeña semblanza del doctor tanto del doctor Machacek como el doctor Staubach. El doctor ingeniero Jan Machacek es consultor y jefe del área de geotecnia numérica en la Technische Universität Darmstadt. Su investigación se centra en el desarrollo de métodos numéricos para una amplia gama de aplicaciones en ingeniería geotécnica, con énfasis en procesos acoplados, formulaciones avanzadas de elementos finitos, suelos parcialmente saturados, cargas cíclicas, simulación de grandes deformaciones y calibración automática de parámetros. El profesor doctor ingeniero Patrick Staubach es profesor de geotecnia en la Bauhaus-Universität Weimar. Su investigación se enfoca en la geotecnia numérica, con especial experiencia en mecánica de contactos, cargas cíclicas, sistemas hidromecánicos acoplados y modelado de grandes deformaciones. Doctor Staubach, adelante.
Yeah, thank you very much for this introduction. I'm very happy to be allowed to present here our numerical framework NUMGEO. I will give today an overview over the software, and we will also focus on application, particularly with the focus on slope stability and also groundwater flow. I give this presentation also on behalf of Jan Machacek from Technische Universität Darmstadt, who has just been introduced. And there's also a number of other people who have contributed to NUMGEO over the years, which are listed here below. So what do we want to discuss today? First, I want to give an overview over the software itself. And we want to discuss about pre- and post-processor options for the software, because NUMGEO itself is only a finite element solver. So you still need to somehow create your model in a preprocessor, and then you have to post-process it with another software. And I will show you how to actually do that. Then we want to discuss what is upcoming. We do periodically some releases, and it may be of info or interest to you what are the next steps with the software. In order to show you the capabilities of the software, I will present ongoing developments in terms of research. So you will get an idea what are the basic and the advanced capabilities of this software. And this will go hand in hand with some application examples. And then at the end, because it was one of the topics that we decided to focus on, we will discuss how to perform strength reduction analysis with the software NUMGEO. Let's start with the overview. So NUMGEO is a standalone finite element code that Jan Machacek started to develop in 2017. At that time in Karlsruhe, he later then changed to Technische Universität Darmstadt. I joined development of NUMGEO in 2019, and nowadays I'm at Bauhaus University Weimar. This is BUW. And in the meantime, there are a number of additional people who have joined us in the development of the software from different institutes, mainly from Ruhr University in Bochum, and they have all contributed to the code. And the way we will present the code is depicted here on the left side in these circles. So the inner core is basically the way that it's programmed. It's modular programmed in modern Fortran, and we will particularly focus here on the outer circle where there are the geotechnical relevant implementations. You can get more information about the code from the website, which you might have seen, and we also have an HTML documentation which you can find more information. And during this talk, I will refer a lot to this documentation. Most importantly, probably to mention is that this is free software. So we have developed it while working at the university, and therefore it's a free pre-compiled finite element software. We do offer it for downloads, and we also monitor the downloads. So to get an idea, we have several thousands of people who have downloaded it from several hundreds of institutions and more than 30 countries. Now it's a pre-compiled program, so it's not open source. We do make it open source for people who are collaborating with us, where we do believe that they want to enhance the implementations, who want to substantially contribute something to the source code. And there we have collaborations with UBC Vancouver, but also, for instance, with University of Western Australia, where the code is also used and also partly developed. This was the general overview. Let's first start here with the first outer circle, which is which finite elements do we offer. This is the basis of a finite element code, the finite element formulation that are offered. And the way we structure our finite element formulations is according to the number of active phases that you are considering. So you can have a one-phase medium that can be porous or solid. Think about a dry soil, or think about a structural element like concrete. And because it's a geotechnical code, we have focused a lot on multi-phase element formulations. And for two phases, this means it's the solid grains, and then around the water, we have multiple finite element formulations. And they are named according to the variables that they spatially discretize. So all of these finite elements discretize the solid displacement. This is the bold U, but they in addition also discretize some variable of the pore water. The most common formulation that I'm sure most of you are familiar with is the UP element formulation, where in addition to the solid displacement, the pore water pressure is spatially discretized. This is the most common formulation. It's also implemented in most commercial software like this, for instance, in Fluxys. There are different ways how to implement this UP element formulation. The most common is the Taylor-Hood formulation, but there are also stabilized formulations of this element type, because regularly you cannot interpolate displacement and pressure with the same order. This is basically captured in a Taylor-Hood formulation by discretizing the displacement one order larger than the pressure. But this can be resolved, for instance, with mini or FPL stabilized UP element formulations, which are all implemented. The advantage of these mini or FPL stabilized formulations is that you can use linearly interpolated displacement elements with linearly interpolated pressure. That can be of advantage. Now, formulations which you might not be so much aware is that you can also spatially discretize displacement of the water phase. Now, in the UU formulation, we would spatially discretize the displacement of the solid phase and the displacement of the water phase. The underlying equations, the differential equations, are the same as for the UP element formulation, but we just decide to spatially discretize another variable. This has important implications for boundary conditions, but also some assumptions that you have to make about the differential equation. And we will later show that this UU element formulation or the UPU element formulation can give you more flexibility when it comes to certain boundary conditions that you might not be able to resolve with UP element formulations. Now, coming to the unsaturated phases, if we do have three active phases, we also have a continuous air phase in between our continuous water phase. And then we, in addition, also do need to discretize the pressure of the air. So this allows you the full unsaturated capabilities. And finally, you can even go one step further and you can introduce 4 phases. So for instance, you could consider for unsaturated conditions, even if you increase suction a lot, there is some residual air which is still attached to your individual grains because it cannot basically move away from, or it's enclosed and it cannot get mobile. And this can be incorporated with 4-phase finite elements. And for instance, you could also model expansive soils with this formulation. Now, all of these formulations, they work for static, transient, but also dynamic analysis. So for each of this finite element formulation, you would also be able to perform, for instance, earthquake analysis where you want to consider inertia. Coming to the element formulations from a visual perspective. So we do offer 2D, axial symmetric, and 3D elements with various interpolation orders of the different variables, which is basically indicated by the different node number that exists, and also with different integration rules. So the integration points are here with the blue crosses inside of the element. So for some simulations, reduced integrated elements are favorable. They are also faster, and those elements can then also supplement it with hourglass stiffness in order to counteract any zero energy modes. And on the 3D finite element formulations, we have tetrahedric elements, and we have also hexagonal elements with different interpolation order. The second important part for geotechnical engineers next to the element formulation is the mechanical modeling that we offer. So we offer a wide variety of constitutive models to be used. Here at the top, we start with very basic models. So of course we have linear elasticity, this is LE, and we also have more Coulomb in various implementations. We have modified calm-clay models, and we have all the plasticity, the basic plasticity models that are used particularly in practice. But because we are also a research code, we have more advanced constitutive models. In particular, in Europe, hyperplasticity is very commonly adopted. We have it conventionally with the intercondylar strain extension and also with the more recently developed ISA extension. And then we also have partly the sunny sand family. The sunny sand family nowadays is quite large. We have the basic model from 2004, but we also have more recent developments of that sunny sand model, particular for cyclic and also semi-fluidized states. And finally, there's also a particular plasticity implementation for unsaturated soils. This was now the advanced constitutive models for non-cohesive soils. So in the green box, you see those models for cohesive soils. And we do have the clay hypoplasticity model by David Margin, and we have also the Avisa model from Arita Tafili, and there are other cohesive models as well, for instance, one for expansive soils. A special feature of NUMGEO is the simulation of high cyclic action. So we roughly say high cyclic loading is loading with more than 10,000 cycles. And for this high cyclic loading with a very large number of loading cycles, think about traffic loading, but also think about wind or wave loading, we need special constitutive models, because nobody can simulate millions of loading cycles with the top constitutive models that I have just introduced. And here we have the high cycle accumulation models. They work differently than the conventional constitutive models. They only predict the average trend during cyclic loading. So you are not following the individual cycles with these constitutive models, but you are just predicting the average trend, because at a large number of cycles, nobody really cares what happens during the cycles, but what happens in average. And for this, we have the high cycle accumulation model for sand and the one for clay. If you are familiar with these models, you might know that they need as an input variable the strain amplitude from an individual loading cycle. And for this, you need one of these above conventional constitutive models. And here we offer some of the advanced constitutive models listed above. in order to calculate the strain amplitude used as an input for the HCA models. The next thing that I want to discuss are hydraulic models, which you would need when it comes to modeling of unsaturated soils. In this case, you have to describe the soil water retention curve, and we have a number of models which you can adopt to supplement this constitutive relation. At the same time, you have to account for a relative permeability. So if you have unsaturated conditions, the hydraulic conductivity of the water through the skeleton will be lower. And there are also a number of models to consider this. And finally, you also need to account for the effective stress formulation if you have unsaturated states, to account for suction. And there are also a number of models from which you can choose in that software. Finally, in terms of permeability in general, we do have implemented a porosity-dependent equation by Kozeny-Karman to account for a reduction of permeability if, for instance, porosity decreases when you have some volumetric strain leading to compaction. Important aspect of finite element simulations are interactions. So we do allow in NUMGEO that multiple parts of your computational domain are interacting with each other. And we allow for large deformations between objects and also arbitrary meshes between the objects. So we are not like Plaxis limited to very simple spring interaction between nodes with some discrete interface elements, but we have state-of-the-art contact discretization methods for this. And the state-of-the-art contact discretization methods are so-called mortar methods. Here on the right side, it's schematically shown how those methods work and which advantage they have. Consider if you have a structure in gray coming in contact with soil in yellow, this formulation will project the nodes of the facing edges on the edge on the other side. And then in between this projection, you add a lot of integration points. And at each of this integration point, you determine the distance between the two surfaces, between the two objects. And then you also calculate contact stresses based on that refined distance. The great advantage of this is that you are able to resolve the surface very accurately. So if the two objects have very different surface shape, you are still able to calculate rather precisely the distribution of contact stresses between those two surfaces. And what it allows you numerically is that you can model large relative displacements. So there is technically no limit in the tangential relative motion of two surfaces. So for instance, Abacus common finite element software would denote this as a finite sliding algorithm. This is advantages. And at the same time, this method also resolves mesh dependency. So you do not have to account that the two surfaces have to be meshed very similarly, but this method resolves the mesh dependency by using this higher resolution by these red crosses indicated here. This basically calculates you the normal contact stresses, so it makes sure that the two objects are not intersecting each other. However, we still need to describe how does the surface behave from a constitutive point of view. So you can adopt a simple Coulomb friction model but what is often observed in interface shear tests, that the behavior of soils in an interface, so for instance with concrete, is more complex. So the interface behavior actually is very similar to the continuum behavior. So we see a clear dependency on the density. for instance. And the idea in NUMGEO is that in the interface zone, we use also one of the sophisticated constitutive models that I have introduced before. So for instance, sunny sand or hypoplasticity to, for instance, account for the density effect also in the interface zone, but also for cyclic loading. If you have cyclic interface shearing, it's advantage to use one of the more sophisticated constitutive laws. And at the end, between or next to all of these very sophisticated models, we also offer a classical node-to-node contact discretization. So this is very similar to what is implemented in most common finite element software, where between the nodes you are basically implementing springs to account for the contact interaction. Finally, we also want to say a few words about boundary condition, but we don't want to cover it all here. We only want to highlight a few aspects of the codes because boundary conditions are quite broad topic. So what we offer built in are the generation of random fields. They follow a Markov correlation. What you give is basically the minimum and the maximum value of some field that you want to spatially distribute, and the correlation range. So the correlation range basically determines you over a certain distance how large is basically the correlation of the values that you are distributing. We have that built in, but we also have it externally by means of Python codes. So I will come to that in a second. With NUMGEO, you can also read in, for instance, arbitrary initial conditions. So you could also generate these random fields with an external script, say it's a Python script, and then you import it into NUMGEO. The Python scripts that we are also offering, they allow a little bit more flexibility. So for instance, cross correlations. If you want to link also, for instance, the friction angle somehow with the initial density. If all of this is not enough for your application, we do allow to modify the code with user subroutines. User subroutines allow you to basically program your own code and have it incorporated in our pre-built program. Let's have a look here in our wheel which routines you might want to modify. So we offer the modification of the material. You are allowed to completely code your own user mechanical model, and the interface, if you are familiar with Abacus, UMAT, it's very similar to that interface. And it's also possible to link it with user subroutines that have, for instance, been programmed in Fluxus. You can also do that for unsaturated conditions, and you can also implement your own user contact properties. So for instance, if in one part of your model you want to use different contact friction angle in another region than your model, you can do that very flexible with user contact properties where you have some dependency on coordinates. Important aspect are the initial state conditions. We allow users to define initial states, initial stress, initial void ratio through user subroutines. So for instance, consider the initial stress conditions in on slope. We don't have a pre-built initial stress condition for that. You could basically apply gravity and then the stress will come into equilibrium, and then you will get a stress distribution which is in initial equilibrium. But you might also want to initially define it, the initial stress conditions for slope, for which you could use this in user initial stress user routine. You can define user amplitudes. So for instance, if you have very strong changes with time and an amplitude, for instance, consider a recorded train loading that you want to apply as a loading condition. And you could read in this signal that you have recorded. And finally, you can also modify boundary conditions, and you can also modify loading. So you could apply a user loading, which depends on a number of factors. So for instance, a user loading, which depends on the coordinates, for instance, to consider some linear decreasing surface loads. Now let's come to the actual application of the software. So as it is currently, we are offering the software for Windows and also for Ubuntu, where more Linux-based operating systems are pending. In Windows, you have two different options to adopt the software. We offer a portable version. The idea of the portable version is you don't have to install anything. If you download it from our website, you get an executable. That's the NUMGEO software, and we do ship a number of DLL files with it that you need to execute NUMGEO. Technically, these DLL files, which we are shipping together with NUMGEO, there are about 10. They have to be located in the calculation folder where you execute NUMGEO. If you get tired of always copying the executable together with the DLL files, you can also put up a system variable in your system path so that Windows always finds them directly. This portable version is very nice because you don't need to install anything, and it doesn't require any space on your system. The shortcoming is that the user subroutines that I have presented on the slide before, they require a compiler. Of course, if you program something, you have to compile it in order to have it read by NUMGEO. In this case, you might come away with an option like MingW, which works as well. So you could compile these user subroutines with MingW, and then also NUMGEO can read it. But if you don't have that, then you cannot use user subroutines. To be honest, you don't need user subroutines so often. So the simulations we do, they do not always require user subroutines. So you might be fine using the Windows portable version at the start. The alternative is you do a full installation under Windows, which basically means you need to install the same software which we are also using for developing NUMGEO. And this is Visual Studio and Intel One API. They are nowadays completely free. You can download them for free. And from my perspective, they are also very good for developing software, but they require a lot of space. So you can calculate with about 10 gigabytes that you need. And in this case, you have the full installation, which also means you can out of the box compile user subroutines in case you want to. Then coming to Ubuntu, originally NUMGEO was developed under Ubuntu, but we have then later on moved to Windows again. So in Ubuntu, you do need to install either Intel One API or GCC. So there is no portable version for Ubuntu, but once again, these two softwares, they are free. And then you can also directly use user subroutines. And finally, we did get some questions about Fedora, for instance. So it's currently not supported with the software that you can download, but actually we have now resolved it for Fedora. So in the next release, it will also work with Fedora. We have very broad documentation. Here on the right side, there is an example of our HTML documentation, and this documentation is split into an installation manual. In the installation manual, you find all the information that I have just summarized on the previous slide. Then there's a reference manual. The reference manual shows you all the features that are implemented and how you can use them in your simulation. So this is what is just shown there on the animation. And it's very nice in this documentation. You can search after keywords and you are directly prompted then to the respective command. There's also a theory manual. So if you want to know how certain things are implemented, you can have a look at the theory manual. There you find equations for most implementations that are incorporated in NUMGEO. Finally, we also have a verification part. This is the benchmark part here in the documentation. There are comparisons of our code with analytical solutions and also commercial FE codes. So there you will find a number of benchmarks for various problems where we compare our code to established codes or analytical solutions. And most importantly, probably for the application part are tutorials. We have 19 step-by-step tutorials. So they guide you to example problems with different level of complexity. And this is also what I will show you in the next part of the presentation. There I will show you examples, which in parts are also tutorials, which you can follow in order to get to the point where you can set up your own model. And we will also add more and more to those tutorial sections in the future. Now let's come after discussing about the core program about how to perform pre and post processing. Here are the 3 steps that you need to undertake to do a simulation with NUMGEO. So the first step is pre-processing. And the basic way how to do that with NUMGEO is script based. So here there's an excerpt from such a script where you have to basically follow our way that we have defined comments. It is the same way that you would define an input file in Abacus. So if you're familiar with Abacus, then it will be very easy for you to get to know to NUMGEO. So the comments are mostly the same. You can look up all of these comments that you see here on the left side on the reference manual, and you have to set up your mesh, or you can set up your mesh using various preprocessors that are available. I'm a big fan of Salome. Salome is also free to use and has a lot of capabilities. We use it mainly to set up the geometry and then also create the mesh. But you could also use Gmesh to do that. Once you have created your input file, you can start the calculation with NUMGEO. If you did something wrong, and I'm sure you did something wrong because I also do something wrong when I start a calculation, then NUMGEO will issue some kind of error message, which will give hints what is wrong. And this can take some time because it's a back and forth. You have to check what is the error, what did I wrong in my input file. And then finally, if your simulation runs, you can start the post-processing, and we do use ParaView for visualization of fields. So here is an example for laterally loaded piles, which is animated with ParaView. ParaView is also free, and from my perspective, it's probably the best post-processor which exists. At the same time, we are also offering so-called print output. This is, for instance, the displacement history at one node. So you can set in the input file the definition to have at certain points information directly printed out in tables. So in this table, then there is directly a graphical representation of some time history possible. So this is not necessary to do in ParaView. You can directly, for certain points of your finite element model, get time histories. For instance, settlement at a foundation, you directly get it as a tabled value. We do know that this kind of pre-processing can be unhandy, for why there is NUMGEO GID. You might be familiar with GID. It's a very powerful CAD and mesh software. And it also allows you to incorporate program-specific commands and keywords into the software. So what was done is that in GID, there's a program type which is NUMGEO. And from our website, you can download this program type and incorporate it in GID. And then in GID, you can do a guided pre-processing. I will show in a second how that works. The rest of the steps remain the same, but you can do the simulation or the calculation directly from GID. So you can start the simulation in GID, you will get information about how your simulation is going, and at the end, you can also visualize it with GID. Here is the program or the program interface from GID, and you have different sections of that program interface. You have here the data tree, and in the middle, in the sketch area, you have the model that you have generated. GID works with layers and groups, which you can activate and deactivate in order to, for instance, to deactivate the soil here to only have view on the pile area. And in this data tree, you are guided through the generation of your finite element model. So all the steps that we have also discussed now from an implementation point of view. So for instance, element type, material assignment, it's all guided. So you cannot do as much wrong as during this input file setup. And each of this individual topic has smaller sections where then you can do a lot of fine-tuning of the different settings. And this really, I think, enhances the user experience. They are only relevant settings which are displayed at the beginning in order to streamline the user experience, so that you are not like having hundreds or thousands of options and you do not really know if you have to fill them out or not. So at the start, it's all streamlined for the user. And then you have assisted generation of material definitions and initial conditions, for instance. So here's an example. If you have picked hyperplasticity plus intergranular strain as constitutive model, then directly here the list of parameters that you do need for that constitutive model are given to you. So you're not missing to define any of these parameters. So there's also an easy assignment then of the materials and the initial conditions to your FE model components. This is here on the right side shown for a cantilever wall, for which at the end of this presentation, we will also see some simulations using strength reduction method. And there is also a transparent access to more advanced settings, like for instance, if you want to change the solver selection, or what you probably want to change very rarely is the convergence criteria. It is modifiable, but technically you never do need to modify, for instance, convergence criteria. Now let's come to what is ahead. As I said, we are doing regular releases where the software is periodically updated. Here is a short overview over the releases that we did in the last year. So they tend to get a little bit more frequent because we, at least I hope so, we more frequently add more features, and we also more frequently do bug fixes because we also have more contributors. Now in August, mid of August, we are planning a new release. For instance, in this release, we will include structural elements. This is something, a very basic feature, which we didn't have up to now. So beginning with August, there will also be structural elements available. There are general modifications, and there are also more content to manuals to be added. And normally there are also some bug fixes, which we are reporting there. You can find the full release history also in our documentation. So for each of these years and months, there's a list of changes which we did to the software, so you can keep track on the changes that we did, and maybe you also need to react to those changes when you download a new release, but you want to use old input files. Now let's come to some ongoing developments, particular with aim on research. The idea here also is to show you some capabilities of the software that we currently have, and then we will follow that with the application examples. So one very large recent research project is NUMGEO PFEM. PFEM stands for Particle Finite Element Method, and it's a method for large deformations. I will talk a little bit more about modeling large deformations also on the examples. So at the moment, NUMGEO only allows for updated Lagrange simulations, but we don't have really something to model really large deformations. So where, for instance, you need remeshing. PFEM is a very intelligent way how to perform remeshing. The calculation cycle is shown here in this picture. So in PFEM, you start with a cloud of points, which is denoted as particles. In each calculation cycle, you reconnect these points with a triangulation scheme to generate your finite elements. At the borders, you typically have to apply a shape, an alpha shape algorithm, in order to have the situation which is depicted here, so that there are remaining some unconnected nodes. Then the information which is stored in nodes in the particles for the numerical integration and the calculation of the updated stress is first mapped back to integration points, and then NUMGEO is performing the full analysis using conventional classical FEM. This is the large advantage of PFEM. Basically, it's classical FEM plus this triangulation scheme and the mapping from particles to integration points. Once you have updated the information on the particles, so you have updated displacement, but also the strains in the integration points, you map back this information to the particles. And as a very special feature, this PFEM is developed for different drainage conditions. So you can also do partially drained simulations with this implementation in NUMGEO. And you have a number of different finite elements that are possible. So that we do not only offer first order triangle elements, as it is typically done with PFEM, but also rectangle or second order elements. And also in NUMGEO, there's a novel approach to transfer these data variables from the particles to the integration points. Now, how is that helpful? For instance, here on the right side, you would need such large deformation technique to model cone penetration testing. And here on the right side, you see how a cone is pressed into an undrained cohesive soil. It's modeled with Tresca in this case. And you see that periodic reconnection of the particles to triangles around the cone. And this is a classical benchmark simulation used by the community developing large deformation techniques. And on the left side, this simulation is performed for difference ratios of the shear stiffness to the undrained cohesion, plotted versus the cone factor NC, which basically relates here the cone stress minus the initial vertical stress subtracted to the undrained cohesion. And here we have plotted a number of researchers with various codes for large deformations for this type of simulation. And we have compared the PFEM method with the so-called SIPA method, both implemented in NUMGEO with various other solutions. So the SIPA method I will introduce later. It's also performed in NUMGEO. It's another way to simulate this problem where no remeshing is performed. And we compared that with material point method and also coupled Eulerian-Lagrange method, and we found a very good agreement with the solution of NUMGEO with the other codes. Here is a comparison for the cone penetration test in sand. We see here with depth the cone factor QC and also the friction ratio Fs, and the different implemented schemes for the PFEM method are compared, and they all have a very good agreement with model tests from 1991 as depicted here on the right side. Now coming to a totally different topic. We are now moving away from the PFEM to NUMGEO ACT. ACT stands for Automatic Calibration Tool, and it's a software which is used to calibrate constitutive soil models. And it does calibrate the parameters of constitutive soil models by means of an optimization algorithm. So it's completely automized the way that the software tries to find an optimal solution for the parameter set. Here it's displayed how this works. You need to have your experiments, of course. The experiments could be odometric tests, could be trained or untrained, monotonic or cyclic triaxial tests, or it could also be shear tests. Then we first adopt some constitutive model. It's more or less arbitrary what you pick here. It could be hyperplasticity, it could be sunny sand. And we first estimate a set of parameters. We perform a simulation of the tests in the data bank, and then we compare the curve from the simulation with the test from the physical testing. Then you need to quantify the difference between the simulation and the test. There are different ways how to quantify that. There are a number of different methods implemented in this ACT method. You then calculate a weighted error, and eventually you set some error tolerance. And if your current error is below the error tolerance, you have your final set of parameters, and hopefully it fits very well. Otherwise, you have to optimize the parameters. And this is done with some automatic optimization algorithm. There are a number of algorithms implemented in this ACT software. So for instance, it could be the DE, differential evolution algorithm. And at this point, Jan Machacek joined our presentation, and I think it's a very good slide to hand over to Jan, because NUMGEO ACT is more or less his project, also with his PhD students. So Jan, if you are ready and set, then I would hand over to you at that part, and I will go forward in the presentation.
Yeah, okay. Thank you very much. And also, sorry for my delay. So where exactly have you stopped on this slide?
Okay, if you haven't witnessed it, I have tried to explain the full circle, and I ended at the optimization algorithm. Okay. Maybe people can ask afterwards, it was not clear what I have presented, but feel free.
Okay. Yeah, so the main idea of the automatic calibration process is to mimic the behavior that a usual engineer would take in order to calibrate the parameters, but just to replace the iterative refinement by a clever optimization algorithm. And for that, we can use different approaches like particle swarm optimization, which is a PSO given in the brackets, differential evolution, or genetic algorithms. But what we've found so far is that if we want to calibrate cyclic tests, so the parameters, for example, for a sand model or a hyperplastic model with intergranular strain, then the standard optimization algorithms, they do not really perform so well. We find quite a large scatter if we repeat the calibration multiple times. And for that, we developed our own optimization algorithm that performs a bit better in that regard for the cyclic loading. And this is then called the differential evolution with elitism and multipopulation theme. And so that's our standard approach for doing that. So if the calibration or optimization algorithm finds a suitable parameter set at the end, so this is determined, for example, if we fall below a threshold in terms of the cost function value, which is denoted here with the delta epsilon, then we deem the calibration to be finished, and then we think that we found an optimal parameter set. So now you could switch the slide, please. So we have one example for you to showcase maybe that a bit. So if you go back, please, one slide, that was one too fast. Where you can see for one specific material, so that's a fine sand that we see here, we have multiple tests. We have an odometric compression test. We have grained monotonic triaxial tests. We have also ungrained monotonic triaxial tests and cyclic ungrained triaxial tests. And you see also that for each test type, we have multiple of different experiments. And now we are looking for the one parameter set for the hyperplastic model that fits best all of the experiments. And that is this process is then shown on the next slide, where you see the progress of such an automatic calibration. You see the drop in the cost function. The cost function quantifies the difficulty between experiment and simulation. You can see the simulation results are given all in the black curves, and the experiments are given in the dashed colored curves. So a high cost function value denotes a rather bad fit between the experiment and the simulation, and the lower the cost function gets, the better is the agreement between both. And you can see at the end of the calibration process, we have quite a good agreement for monotonic tests like the ergometric compression test, but also for the cyclic tests given in the bottom row. Now, obviously, this is the element test level, and the question is how well do these automatically calibrated parameters perform in boundary value problems? And that is shown on the next slide. So we tested this approach on different boundary value problems of different complexity. On the left-hand side, so the first box shows you the monotonic horizontal loading of a single pile. The second box shows you an embankment of saturated sand, which is excited by an earthquake loading at the base. And the third box on the right-hand side gives you a sheet pile wall, and that is again loaded by an earthquake loading. And you can see in all three cases, we performed numerical simulations. The black lines in these plots always showcase the method data from the experiments, and the colored lines give you the simulation results. And you can also see, for example, for the single pile, that there are multiple simulation curves. So we repeated our approach for the whole calibration up to 50 times to see if our approach is robust in terms of the prediction. And you can also see that for 50 different calibrations, we get nearly the same result in terms of the predicted outcome in the boundary value problem, which shows that the robust framework and the process that we developed here is rather robust. Next slide, please. Now, as you might have seen so far, is that the NUMGEO framework was developed in terms of text-based inputs. So we started also interfacing it with the GID software for graphical pre- and post-processing, but there are some tasks that can be further optimized, and that is, for example, given for monopiles, especially in the context of offshore geotechnics, where we are, for example, interested in how the pile deforms under several thousands of loading cycles, maybe up to millions. Now, in this case, the numerical models itself, they are, from the geometry-wise, rather simple, but creating these models and matching might take some time. So we created an application that allows you to do that parameterized and to quickly, in a matter of minutes, create such models for monopiles. Next slide. So now I think it's up to you again.
Yep. So Jan has just introduced a pile model, and we want to continue with this boundary value problem. And what we have discussed not so much up to now is the time integration that NUMGEO is featuring. And we do not only in dynamic analysis allow implicit time integration, but also very efficient explicit time integration. And in addition to this, we allow for spatially mixed implicit explicit time integration. The idea is as follows. We in geotechnics, we often have very stiff structures, and the soil in comparison is rather weak or soft. Now in explicit dynamics, the critical time increment is governed by the stiff structure. And we want to optimize this by only simulating the part of the soil in an explicit time integration scheme and solve the structure still in an implicit time integration scheme. We can then use very large time increments because the time increment is no longer limited by the critical time increment of the structure. At the same time, using implicit time integration for the structure is unconditional stable. So technically, we get a stable solution independent of the time increment. But for the soil, it's extremely fast to use explicit time integration, in particular because the soil typically has more degrees of freedom than our structure. And we have implemented that in NUMGEO with full hydromechanically coupling for the soil. So you can solve the soil zone considering the coupled element formulations that we have initially introduced. When does this, for instance, come in very handy? Dynamic pile loading, for instance. Here you do want to consider the self-deformations of the pile. You do want to analyze wave propagation through the structure. So we actually solve the pile in implicit time integration and the soil in explicit time integration. And we do solve that in one global system of equations, which is shown here on the right. And you also see that in this stiffness matrix, the implicit part is much denser than the explicit part. In fact, the explicit part is basically diagonal. This is why it's solved so fast. We have compared the solution of this IMAX scheme for dynamic pile testing, and we found very good accordance between full implicit time integration and this IMAX approach, both in pile displacement, but also in pore water pressure distribution or development in the soil. And the speed up is of factor 10 to 100 to a full implicit simulation. What are further applications? So this is not only relevant for pile dynamic loading, but also, for instance, if you want to simulate earthquake analysis with a soil structure interaction, then this comes in really handy and you can consider the self-deformations of the structure in the soil. And in general, just large-scale soil structure analysis, there you really should, or one should consider relying on explicit solutions because they are so much faster, because the solving process literally takes no time. Then finally, in NUMGEO, you can also do some kind of discrete analysis. We have not implemented a conventional DEM algorithm, but we have implemented a so-called finite discrete element method. Now, in the finite discrete element method, we make use of those sophisticated contact discretization schemes, the mortar methods that I have introduced earlier. They allow so much flexibility that you can technically also perform such analysis of a very large number of particles interacting with each other. But each particle is individually connected with finite elements. So basically, it's a finite element analysis with a lot of individual particles which are interacting with contact discretization schemes. Why do we do that? Well, you can model arbitrary particle shapes, as you see here in the animation, and you can also adopt constitutive models for your particles. The particles can have plastic deformations. They can have some effects of grain crushing also incorporated. And we are analyzing stresses. Here on the right side, you see that in a simulation with thousands of particles, we can analyze stresses in particles, and that's very attractive for the interpretation of lab tests, for instance. Now we want to come to more application examples to further show you the capabilities of the code. First, we want to introduce some back analysis of vibratory pile driving that we did. Here we do simulate a small scale model test on vibratory pile driving, which is sketched here in the middle. The pile has been driven with a very small vibrator, force driven with 25 Hertz into water saturated sand. And we did simulate this in a large deformation framework, updated Lagrange, here on the simulation on the left side. And this is the so-called zipper method that I introduced earlier. So we are not actually creating a new mesh, but we have created the geometry in a way that this pointed vibrator tip can push the soil to the side. And then we adopted the different finite element formulations we have implemented in NUMGEO. I initially introduced the UP element formulations, and I said they are lacking some of the features of the UPU element formulation. And in this case, the problem with the UP element formulation for this particular boundary value problem is that it neglects the relative acceleration between solid and water phase. And this is very relevant for high frequency problems as it is in vibratory pile driving. So we did investigate this with the full UPU element formulation who does consider this. You see here that the normalized pile penetration, this is this U with the till on top. It's basically the pile penetration divided by its diameter over time of vibration. Fits very well to the experiment. But we also do get the pore water pressure distribution here measured in this red circle in the center of the model very well with both element formulations. And while initially we were aiming for a different result, so we did thought that UPU element formulation will give different results because it does not do this simplification as the UP element formulation does. Eventually, it's a very nice outcome because the UP element formulations are actually much simpler, much faster. And therefore, we concluded that for this problem type, UP element formulations in terms of relative acceleration are sufficient. However, there's another aspect to such kind of problems, and this is the interface between the solid grains and the water phase. Now, during vibratory pile driving, the pile will move up and down, as it is shown here on the left side. Now, the question is, in the upwards phase, what happens with the different phases? Technically, only the water phase should follow the pile, not the grains. The grains should only move upwards because of the flow, of the groundwater flow, but not because it is linked to the pile in any case. Here on the right side, it's schematically shown what we as engineers have actually to define in our numerical model as conditions between soil, water, and structure. Consider a sphere which is uplifted. So you could have cavitation, and then you have a void hole below the sphere and your porous media. If you don't have cavitation, the hole might be filled with water, as it is the case with vibratory pile driving. But if the soil is adhesive, then it should lift up with the sphere. And this is something that you can normally not model with conventional finite element software. And for this, we have implemented a multi-phase contact formulation where you can actually enforce only the water to not separate from the structure. And this actually matters a lot for the simulation, for instance, of vibratory pile driving. Here we see again the pile displacement with time of vibration for the first 12.5 cycles. And while our simulation in red, where we enforce the correct contact conditions, does converge very well and fits the experiment reasonably well, the simulation where we do consider no separation conditions between both the fluid and the solid, and this is what you could do, I guess, with all software which is out there, but you could never do that red simulation. It doesn't work well and it doesn't converge. And we can also show it micromechanically here on the right side that this enforcement of the contact constraints matters a lot. We see here around the pile tip incremental deformations of the solid grains. They have been obtained with high-speed camera. So during the uplift phase, we see in these colored lines the displacement that the solid grains undergo during uplift of the pile. And while the formulation where we coupled grains and water at the pile overestimates the solid displacements, it does not in case we only couple the water phase, because there the grains are not forced to move upwards with the pile. So it is a modeling choice, which is actually of great relevance for some problems. How do you account for multi-phase interfaces? And this is something that you can do with the software. This is also relevant for suction caisson foundations for offshore wind farms. Here, the suction caissons, when subjected to tension, they also lift up. And once again, we have the question, how do we model this uplift? Conventionally, with UP element formulation, you can only consider that the mixture moves up with the suction caissons. But in reality, there's a water gap forming, and you can consider this with the UU and UPU element formulation. We show that here for centrifuge tests on caissons subjected to vertical loading into tension. And actually, this vertical loading has been performed cyclically. So it's a high cycle analysis where on the left lower corner, there is the history of the cyclic load applied to the suction caisson. And the cycles had different amplitudes. At the end, there were amplitudes which were very large to model a storm event. And we can show that only with the elements considering this gap formation, we are able to somewhat predict these results of the centrifuge test. So with the UP element formulation, you are not able to get that uplift behavior during the cyclic loading with thousands of cycles correctly. Another application, but I will only go briefly over this, is ground improvement by deep vibratory compaction. We do that very often, particularly here in Germany, where loose granular soils are compacted with such a vibrator. It's a very complex problem where thousands of cycles are imposed with this vibrating probe. And we did, with the HCA model, with this model for high cyclic loading in NUMGEO, establish a numerical model with which we can model the full process of this deep vibratory compaction, where, for instance, you can estimate the densification and the area of densification around such a probe. Then, to show you the application of this discrete modeling in NUMGEO, we are simulating the installation of stone columns with this method. I have already explained the advantages of this method. The idea here is that the installation of gravel into soft clay, we consider the installation process. And in this case, the method allows that the particles are interacting with the surrounding continuum, and the continuum is the weak soil. So for the weak clay soil to be improved, it does not make sense to model it discretely, so we only model the particles discretely. What we also do with NUMGEO is modeling of infrastructure loading, for instance, by trains. Here is such a 3D simulation of train loading over a discretely modeled track. And we have millions of cycles that we have to consider here. And we consider these millions of cycles with the HCA model that I introduced initially in the presentation. And we also have compared such simulations with measurements that were made here in Germany. So here's a train line, one of the most and strongly driven train lines in Germany, where measurements were made over a span of 5 years. And it was approximately 200,000 cycles that the soil faced. And the measurement was made alongside the layer here in the soil. So we see the distance from the track and the corresponding settlement. And because in our analysis, we did not really know the speeds of the trains, we did different analyses with the speeds of the trains. And eventually we more or less were able to capture the settlement analyses that were taken between these 5 years. Coming now more to the problems that we want to discuss at the end of the presentation, Christoph Schmüderich, who also contributed a lot to NUMGEO, did his PhD on slope stability analysis in residual lakes, which are subjected to earthquake loading. We have this problem in Germany because our coal mining is coming to an end. these open pit mines will then be filled with water, and we get such residual lakes. The problem is that during coal mining, the soil has deposited in a rather loose configuration, and we do have some chances of earthquakes, also in Germany. So we have to make sure, because those residual lakes are rather large, that there will no landslides occur. And NUMGEO offers the possibility to do these dynamic analyses fully coupled with consolidation, with effective stresses. And Christoph Schmüderich has enhanced this by calculating during this earthquake event the factor of safety. He did calculate this factor of safety by doing a strength reduction analysis and during the earthquake calculating factor of safeties. Here we see during this application of the earthquake signal how the factor of safety, which is initially very large, drops because of the earthquake, and at one point it even drops below 1. It's possible that the factor of safety drops below 1 because this is still a dynamic analysis. So even if it drops below 1, because we have inertia effects, it does not mean that our whole simulation doesn't converge any longer. It just means that technically this slope has failed if you set factor of safety as the governing factor there. And we do these analyses by a special feature of NUMGEO. It's called submodel analysis. So during this earthquake, we stop the earthquake analysis. In a second model, we do the strength reduction analysis, get the factor of safety, and then the earthquake analysis continues until the next time step at which we calculate the factor of safety. In relation to the open pit mines, there are also in Germany plans to recultivate these areas by means of onshore wind farms. Now we already have seen on the previous slide that these open pit mines have deposited soil, and currently it's rather unclear if we install onshore wind farms with large piles, how do they act in these very inhomogeneous soil conditions? In particular, because this generation of the artificial lakes takes tens of years, we also have a very long consolidation times of these soils. So technically, we need to build these foundations while consolidation isn't even finished. So what we do numerically is we estimate the lateral loading of the foundations of the onshore wind farms due to wind loading, but also at the same time considering the consolidation procedures in the soil and also considering the inhomogeneous soil conditions. And here, these different lines, they correspond to different soil configurations. So we tried, for instance, clay layers only and also sand layers only, which gives you the lowest rotation. And then in between, it depends a little bit on how these patterns of clay and sand are located. In terms of validation, we also did simulate here a centrifuge test on soil subjected to earthquake loading with a foundation on top. And we compared in a certain depth the excess pore water pressure that is developing during this earthquake loading. The idea here was once again to show the advantages of our more sophisticated element formulations in comparison to the UP element formulation. Once again, we do see some differences between this full UU formulation and this simplified UP element formulation, but overall the discrepancy is small compared to the experiment. And in the animation, you also very nicely see that we can simulate the sliding of the foundation on top of the soil. Then we come to our final topic. It's strength reduction, and I hand over to Jan.
Yeah, so we're coming near to the end, not already approaching the end, but it's at least the final topic. And it's a topic that was especially requested when preparing that presentation here. So the question was about how or if we can treat stability analysis in NUMGEO and how we do it, and especially also if groundwater flow is to be considered. And as most of geotechnical finite element softwares, we can perform stability analysis, and we do so by using the strength reduction. So we determine something called a factor of safety, which is a quantification of the safety margin of a structure by iteratively or successively reducing the shear strength parameters, so the effective friction angle and the cohesion. And we then determine the factor of safety as the ratio of the current, so the reduced shear strength, and the shear strength at failure. Now, in the current version, the strength reduction is only available for more Coulomb, so simple elastoplastic models. We are working also on porting it to more complex models, but that's the current state that is distributed. Now, in order to find the critical factor of safety, we use an iterative process. For that, we start with an initial factor of safety. So, for example, we assume that the factor of safety is 1. In that case, we assume that our system is stable at the beginning, and then we will incrementally increase the factor of safety step by step with small increments. And as soon as we have a point where we have no convergence, so we don't find equilibrium for the current set, so this is the first red dot that you see where we have rejected non-convergence written, we don't abort the simulation. But what we do instead is we go back to our last converged stage, we reduce the increment in the factor of safety and retry that increment once more. And you see now in the example here, it fails again. So what we do is we reduce it once more. We go again back to the converged state and go with a much reduced factor of safety increment in the next step. So then we might be lucky and we have, again, the convergence, we find equilibrium in our system, then we can increase further the factor of safety. Now, this iterative process will continue until we reach a size of the increment in factor of safety that falls below a given tolerance, for example, 10 to the power of -4. And then we say we are accurate enough, and the final value of the factor of safety is our result of the simulation. Now, we brought you here 2 examples for this process, both involving groundwater flow. Now, I have to say that all of these examples have been simulated and investigated by a large group of people, which is mainly, let's say, the counterpart of the Mexican Geotechnical Society. It's a German Geotechnical Society. And there we have a subgroup or a working group that is called Numerical Methods in Geotechnical Engineering. And there we have a subgroup that concerns mainly with geo-hydromechanical interaction. So there are a lot of people using different software, all analyzing the same issues. And the first example that you see here is an embankment of a reservoir that is initially saturated. So we have initially a high water level in that reservoir, but then we have a rapid drop down in water level inside the reservoir. And now we're interested in how the factor of safety of that slope develops during that rapid drawdown. We have considered 2 different scenarios. So the first scenario is very fast drawdown, where we have a drop in water level of 8 meters in 1 day. And the second scenario is a bit slower, where we have 8 days of drawdown time. So it is obvious that these are transient processes that play a role here. The phreatic surface is an unknown in that simulation, so we have to solve for the phreatic surface. And depending on the location of the phreatic surface, we will have different factors of safety. Now, this system has been investigated with different software programs, for example, Plaxis, ZSoil, CSAR, and also NUMGEO, and the results are now shown on the next slides. But before we can see the factor of safety, we first have to have a look at the boundary conditions, because these are rather special in that in that example. So to simulate the drop in water level on the embankment phase, we have to have a boundary condition that changes not only in time, but also in place, right? Because if the water level drops, we can only prescribe the hydrostatic water pressure below the water level. So for that, we have something that we call flexible boundary condition that allows you to prescribe displacements, water pressure, so solution variables, depending on time and space. In the present case, it's a rather simple one. You can see that on the bottom right of this slide, where you see 3 scenarios. In all cases, you see a hydrostatic distribution of pore water pressure. Now, on the left-hand side, it is rather small. On the middle, you see if time progresses, then we have a rise of the water level. So the hydrostatic, or the 0 point of the hydrostatic distribution, is moving in the vertical direction, and obviously the magnitude at the base of the model as well. And so then for the final time, when we reach 8 meters, in this case, we have our final value. So now we can describe spatial and temporal variations in boundary conditions, and we can do the same for this example, just the reverse order. We start at the initial water table level, and then we reduce it in time and space to reach the final water level. Now, above the water level at any time, now you could please go to the next slide, we need to specify some drainage conditions. So you could either assume that it's undrained, so the pore water pressure will freely develop. You could assume to be ideally drained, so following negative pore water pressures, following the linear distribution of the pore water pressure. Or you could use an intermediate type of boundary condition, so a so-called drainage boundary condition. The drainage boundary conditions, they act as an iterative boundary condition. Now, in the present case here is the boundary condition will give you an outflow of water if the pore water pressure is larger than 0, or it will be closed, so undrained if you want to, if the pore water pressure is less than 0, so if you have such partial saturation. Now, with that set up, we can look first at the results. You can see here now the factor of safety on the right-hand side for the rapid drawdown in the top figure and the slow drawdown in the base figure. And you can see the factor of safety on the y-axis, and on the x-axis, you see the groundwater level in the reservoir. So what you can see is, as expected, the lower the water level in the reservoir, the lower the factor of safety. And we can also see, and this is rather nice to see, that we have quite a good agreement between the different software products. So all will give you more or less the same result. Now, after dropping the water level to 21 meters, Patrick, maybe you can change the slide, please. There was a series of calculation stages added at the end, consolidation analysis. So once we waited for 1 day, and then we did the strength reduction. In another one, we waited for 10 days of consolidation, and then performed the strength reduction. And we did so for 1, 10, 100,000, and 10,000 days. The 10,000 days is the steady state that we reach after 10,000 days. And now what we can now track the evolution of the factor of safety during these consolidation stages. And what we see there is that now the differences between the different software projects grow. So we don't have that very narrow band of predicted factor of safeties anymore, but they are still all in a reasonable agreement. So please, the next slide. So the second example that we can show you here is a retaining wall, a backfilled retaining wall that is subjected to a steady state groundwater flow. So now in this example, it was also performed in the same subgroup of the DGGT. We will raise the water table on the right-hand side. So we will show that on the next slide. But what is maybe important to highlight here is that this time we not only included 5 software products, but 8 in total. So what you can see here on this slide on the right bottom boundary is the prescribed hydraulic boundary condition. So we increased the water level from its initial value, which is approximately at the base of the retaining structure. So you see the hydrostatic distribution in a dark blue triangle. And we raised that by 9 meters, by approximately 9 meters to an elevation of 6 meters above the elevation, initial elevation line shown here in red. And then we are looking for the steady state solution, so solving for the phreatic line, and then determining again the factor of safety using a strength reduction. So if we look at the results, what we find there is that we have, compared to the previous result that we saw, quite a big scatter in terms of the predicted factor of safety. So we see that for the initial state, where the groundwater level is at minus 2.5 meters, so this is below the retaining structure, we have predicted factor of safeties ranging from 1.3 to 1.6. And this, one should think that this is the easiest case, since we have still a flat, so we have steady state conditions in this stage. Then we increase the water level on the right-hand side to an elevation of 0, 2, 4, and 6 meters. And we see again a drop in the factor of safety, which is to be expected, but still we have quite a large scatter between the different software products. So obviously the first question was, where is that difference comes from these different software products? And there are multiple small reasons, but one is maybe a bit more prominent, and we can look at that on the following slides. So one idea was to say, well, maybe the phreatic surfaces that are predicted are different, right? So if different parts of the model have different degrees of saturation between the different software products, it would not be that surprising if we have differences in the factor of safety. But what we see here, if we take one specific point of the phreatic surface, and the one that is just below the retaining structure, so shown with that red dot on the small picture, and we evaluate for each water level on the right-hand side, so again at 0 meter elevation, at 2, 4, and 6, and we look where this red dot is in terms of the phreatic surface, we can see that all software products give us more or less exactly the same response. So this is not really the reason for the differences that we see in factor of safety. Now, there is one more important difference between the different software products that we were then aware of. And this is how they calculate effective stress. So if you calculate the effective stress for an unsaturated soil, you have to somehow define how the suction contributes to the magnitude of effective stress. Now, I summarized here the different approaches that are available in different software products. So you can see at the beginning, so this factor chi is actually the factor that weights the contribution of the suction to the effective stress. Nearly all software products allow to ignore the effect of suction on the effective stress. So this is the first column that you see here. You can see that except for the rock science, RS2 and Z soil, all products allow to disable the contribution of suction, which is on the conservative side. Then there is 1 or 2 software products that use the degree of saturation. There is one, or there are multiple that uses the effective degree of saturation. And then there is 2 that allow for the use of a power function for the effective degree of saturation. And you can see that with NUMGEO, we have implemented most of these approaches. We also have implemented some more than the ones given here in the table, but these are the ones that were used in this analysis. But how does this affect the current simulation, and why could that explain the differences in effective safety? Well, if we look what this choice does to the shear strength of the soil, so maybe please you can go to the next slide, Patrick. I try to exemplify that here on this slide. So if you use or assume a Modelon type of material, you can translate the effect of suction to apparent cohesion. So that would simply be, unfortunately, we don't have the equation here, but it is nothing else than the suction times the tangent of the effective friction angle, so tangent of phi, multiplied by this variable chi. And what we see here now is for 3 different approaches for the same soil water retention curve. So the soil water retention curve is given at the top. And at the bottom, we see the magnitude of capillary cohesion or apparent cohesion. And what we can see here is that the choice of this variable, also called Bishop's variable chi, is quite significant in terms of the apparent cohesion. So if we assume that chi equals to the degree of saturation, we can see that already reaching suctions as high as 100 kPa. If we exceed that, we will reach unphysically high values for this apparent cohesion, leading to an overestimation of the shear strength of the soil. Now, if we now go back to the results of our simulations, and we look what different approaches are used in the software, the next slide was fine. You can see the results now classed or grouped by the approach that was chosen for the Bishop's parameter. And now we can see that the scatter is reduced quite drastically. If we compare now the different approaches that we used, we see that we have now a picture or a development of the factor of safety that is actually explainable. And we can also see that assuming that there is no influence of the suction on the shear strength, which is the blue shaded area with the mean value of the blue dashed line, gives the most conservative results, which is in alignment with the theoretical assumptions. So now please next slide, because I think now we are at the end of our presentation. So we hope that we could give you an overview over different implementations, the capabilities, but also maybe some applications of NUMGEO, ranging from research to a bit more practice-oriented examples. So thank you.
Thank you both. Now we are going to start the questions, the Q&A. So first, there are 2 answerable, which was has NUMGEO implemented the PM4 sand, PM4 silt, and HS small or HS brick constitutive models?
Okay, so it's we don't have it implemented yet. So I think that PM4 sand and PM4 silt are maybe the ones that will follow earlier than the HS small. Since for the PM4 sand and PM4 silt, there are implementations available. And so the effort bringing it into NUMGEO is a bit less than that would be required for the HS models. So, but at the current time, it is, unfortunately, I have to say, not yet implemented.
Okay, thank you. And this was another answerable question. It was I found that NUMGEO ACT very interesting and useful. It is a purely mathematical algorithm that, given the range of variation and the model input parameters provided by the user, varies them continuously to fit experimental observations, or is it more than that?
Yeah, so the approach is at the basis, at the core, it is treated as an optimization problem, meaning it is a very mathematical approach. But this is only half of the truth, because we have to define the cost function that tells you how much different is the simulation from the experiment. And there you have to know the laboratory tests, and you also have to know the capabilities of the constitutive model that you want to calibrate. Just as an example, so if you have a semi-sand model, we all know that except for one single model, that's the one proposed by Taludes, all of these models, they behave very poor if you want to simulate an odometric compression test. Now that has to be accounted for during the automatic calibration. right? So you have to know when you define or design these cost functions, you have to know a bit about lab tests, you have to know a bit about constitutive modeling. So it's not purely mathematically driven because there is always some sort of engineering judgment that goes on with such an automatically calibrated parameter set. Yeah.
Thank you.
Okay, I think we're going to give you some questions that have arrived in this section of the chat. Here from Amir Mosaeli, say hi. From Budapest University of Technology and Economics. He wants to calibrate a set of parameters of HCA for Budapest SEM. And the question is, all the tests are conducted and the results are available. How can I use NUMGEO ACT?
So the NUMGEO ACT that we presented here is currently being developed by one of my PhD students and myself, and it will be available once the PhD student defends his thesis. Until then, we don't attribute the ACT, right? So it will be available. I think it will take a year, if counting from now, when we can make it available. But what we do and what we offer so far is that I usually offer to calibrate for you, right? So free of charge. So if you are interested in calibrating a constitutive model for your data, you can send me the data. I will send you a template. You can fill out that template with your lab data, and I can offer you to run the ACT for you. And then you get the results of the ACT. And so that's how we currently deal with the situation that we're not yet sharing it in terms of the code, but we want to make it somehow accessible, right? But we will share it as soon as the PhD student defends his thesis.
Okay, thank you. Rafa, ¿podemos continuar con las preguntas de la sección Q&A, por favor? Bueno, otra que viene aquí en el chat es, what is the name of the model generation tool for pilot plus soil model, and is it accessible already?
So the name was more like monopile modeler. And so we plan to release it in summer, the first version. So it won't be the most beautiful one, but one that will work. It is planned for summer. I'm working on that together with Lucian Canales-Brenner from Ruhr University. So I think that we are finalizing a few steps, and then we can share an early bird version if you want, so, or alpha version that can be used. Yeah. So I think that one goes to Lily. So yeah, we do. But I could actually already send you an executable if you want to try it, but without any guarantee and without any, let's say, bug support or something. So if you just drop me an email.
Okay, thank you. And the last one from the chat, someone asked if you can know the degradation of the concrete pile with the prospection of the example with the pile and the hammer.
If you add a fitting constitutive model, maybe. So technically it's possible because we do consider the self-deformation of the pile and of the stiff structure. So that's the main advantage. But we don't have any constitutive model in NUMGEO to have some structural fatigue effects like in steel, for instance. So that would probably require an own constitutive model to model cyclic fatigue, for instance, of structural elements like concrete or steel. So at the moment, we don't have that, but for pile testing, it would certainly be interesting.
Okay, thank you.
Thank you. So now the next question is, hi, thank you very much for the very interesting topic and for the clarity. I was wondering if you are planning to include NUMGEO any thermal models or thermal coupling?
Yeah, so actually we do. So there is Merita Tafili, who is developing a lot of constitutive models and who is now also delving into the realm of temperature effects on constitutive models. And she has also secured funding to extend NUMGEO towards thermal modeling. So this is something that is currently being worked on by her and her team. And but I can't tell you when it will be ready, right? But as soon as it will be somewhat stable, I guess that it will also be ready or distributed in the release versions. So it is something currently being worked on, yeah.
Okay, next one. What is the name of the model generation tool for pile and soil model, and is it accessible already?
Yeah, I think I answered that already.
Oh, sorry.
It's the Momo tool. I think we had that question already.
Yes,
yeah.
sorry. Okay, here's another one from Jose Luis. Can you perform a probabilistic analysis to evaluate the factor of safety in slope stability analysis?
Yeah, so we can do it, but you have to drive it a bit on your own. So what we can do is we can, I think Patrick showed that, we can generate random fields internally, and we can also create random fields externally using Python scripting, for example, so to create spatial distributions. But there is currently no inbuilt feature that allows you to do the probabilistic assessment. So what you would need to do is maybe write a few lines of Python that does the 100 or thousands runs that you would need with the different random fields, and then evaluate that statistically to get then your 5% of probability of failure or whatever you're looking for. So it is not yet fully integrated at the current time, but it can be used to do so. Right?
Yeah. Thank you. Next question. What constitutive model will be suitable to represent the behavior of expansive soils using NUMGEO?
So if we are talking about expensive in terms of high clay content, sort of mineralogical content that leads to swelling, so volume heave or swelling pressure development, we have currently one model that allows to do so, to model that. That's of hypoplastic nature. We have developed that model on our own. It's called hyposwelling. It is not yet, I think you can't find it in documentation. It will be added soon. So there is a PhD student who will defend, it's Antonia Nitsch, who will defend her PhD this year. And latest then at that point, we will also have the proper documentation for how to use the model and so on. So that's the current state. We have only that one model at the time. So yeah.
Thank you. We have finished all the questions right here. You have responded some on the chat. I have one. Is it possible to escalate this program for multiple CPUs, for example?
Yeah, so you can use parallelization. So currently we are limited to shared memory systems. So we are relying on OpenMP. And by that, you are bound to shared memory systems. So far, it has not limited us because the shared memory systems are growing. So we can use up to 96 cores or whatever your shared system, shared memory system is available to give to you. But we don't use MPI.
Thank you. Which has been the questions for Gianluca Cavallo. which was, is the software scalable with MPI?
Yeah, so as I said, we are relying on OpenMP currently. I think that at some point we will port it to MPI, but currently we're using OpenMP parallelization.
Thank you a lot. So we are now going to Renata, I think we have finished the questions.
Sí, ahora sí puedes leer el reconocimiento.
Sí, de acuerdo. Well, there's just one last question by Vinay Thakur. Can we model the nonlinear variation of suction in unsaturated soils by applying flow conditions?
Yeah, hello, Vinay. I don't know if I understand the question correctly because you could interpret it in two different ways. So do you want to have the loading or the boundary condition being time dependent, or are you interested in spatial nonlinear evolution of the degree of saturation or suction? So I'm not sure in which direction the question is
time dependent. Apparently it's time dependent.
Okay, yeah, so if you have a flow boundary condition, you can model that one as time dependent, right? So you could change the intensity of the flow boundary condition. We use that, or the way we do that is by defining an amplitude that is a series of data points in time that could vary, and we multiply that with a prescribed flow. So if your flow would be, let's say, 1 meter per day, or in terms of the inflow, like a Darcy velocity or something, then you could vary that with any artificial time series. You could just multiply that onto that. So you could model rainfall events, then dry period, and then again rainfall if you want. So that is possible, yes.
Okay, thank you. Now I'm gonna reach the certificate. I'm gonna share it with you. I will obviously email it to you. I'm gonna read it out loud. Let me check. Yes. The Mexican Society of Geotechnical Engineering AC hereby present this certificate of recognition to Dr. Engineer Jan Machacek for delivering the seminar Advanced Geotechnical Modeling with NUMGEO, Capabilities and Applications with Emphasis on Slope Stability and Transient Analysis, by Mexico City, July 21st, 2025. It's signed by our president, Dr. Miguel Manica Malcolm, and our vice president, Master in Engineering, Francisco Alonso Flores Lopez. Thank you a lot. Now for the next one. Okay. The Mexican Society of Geotechnical Engineering, AC, hereby presents this certificate of recognition to Professor Dr. Engineer Patrick Staubach for delivering the seminar Advanced Geotechnical Modeling with NUMGEO, Capabilities and Applications with Emphasis on Slope Stability and Transient Analysis on Mexico City, July 21st, 2025. This is both signed by our President, Miguel Ángel Manica Malcolm, and our Vice President, Francisco Alonso Flores Lopez. Thank you a lot.
Bueno, pues les agradecemos muchísimo la presentación y como pudieron observar a partir de las respuestas que nos dieron a todos, tienen muy buena disposición para que quienes tengan más dudas o quieran tener más datos de sus investigaciones, de su trabajo con NUMGEO, puedan comunicarse o contactarse con ellos vía correo electrónico. Entonces, por favor, los invito a que si tienen inquietud de hacerlo, no duden. Now in English, thank you so much for your presentation. And I was inviting two people to contact you via email for more doubts or to get in touch for more databases or whatever they want to keep in touch with you. But thank you so much for your time and your presentation.
Yeah, thank you for the invitation.
Yeah, thank you very much again It's really an honor, and thank you also for the certificates. That's really something. Thank you.
Thank you. And I hope to see you everyone in Austria next year.
I guess the chances are high. Okay.
Okay.
So, okay. Have a nice day. Bye-bye.
For you too. Thank you. Bye.
See you. Bye.